Good morning, good afternoon, and good evening to all of our attendees worldwide. Welcome to the 9th talk in the inaugural webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. Today's webinar will be presented by Professor Shamsuzzaman Farooq of the National University of Singapore and Nicholas Wilkins of the University of Alberta. I'm Daniel Sidarius of NIST in the United States and Secretary-Treasurer of the IAS. Questions to our speaker will be moderated by Professor Arvind Rajendran of the University of Alberta. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. During today's webinar, questions can be submitted to the speaker via the Q&A tab of the Zoom client or as comments on YouTube. Those comments will be forwarded to the Zoom hosts. Questions will be addressed midway through the webinar and then again following the end of the presentation. I'm now pleased to introduce today's speakers. Professor Shamsuzzaman Farooq is a professor of chemical and biomolecular engineering at the National University of Singapore. He is a fellow of the IAS and the past editor-in-chief of our journal, Adsorption. His research interests focus on separation processes based on adsorption, especially pressure swing processes with applications in energy systems and decarbonization. His excellence in teaching and pedagogy has been recognized through numerous awards. Nicholas Wilkins is a PhD candidate studying chemical engineering at the University of Alberta, under Professors Arvind Rajendran and Stephen Kuznicki. His dissertation research focuses on multi-component adsorption equilibria and diffusion in small pore zeolites, with specific interest in methane upgrading via kinetic separations. Today, our speakers will present on design and interpretation of breakthrough experiments. And with this, I'm going to hand over control to Farooq, and you can start sharing your screen and begin the presentation.
All right, can I just check that all of you can see my screen? And also, you can see that this is
We can see your screen, Farooq.
okay, and you can see that it is changing slides?
Yes.
Okay, very good. Greetings to all the viewers. Trust that all of you are keeping safe and well in this challenging time we are passing. I'm personally very happy to participate in this webinar series, an excellent initiative by Professor Arvind Rajendran and Dr. Daniel Sidarius, and hosted by the International Adsorption Society. My co-speaker today, as you already know, is Nicholas Wilkins from the University of Alberta, and you also know that he's a PhD candidate in Professor Rajendran's group. He brings in a graduate student's perspectives on the nuances of breakthrough experiments based on his recent extensive first-hand experience. We also acknowledge Professor Rajendran's valuable contributions while preparing this talk. Today, we will talk about design and interpretation of breakthrough experiments. We have prepared this talk with graduate students in mind who are new to the field. We have also considered researchers who work on adsorbent development, but also have interest to pursue breakthrough experiments. We will cover how to set up, run, and analyze breakthrough experiments. We will introduce ideas and concepts and illustrate with examples as much as possible. We will focus on gas systems. For fundamentals of breakthrough in liquid systems, please refer to the webinar by Professor Seidel Morgenstern, available on the IAS YouTube channel. We begin with this slide, courtesy of Professor Rajendran, which shows the position of breakthrough experiments in the workflow spanning from adsorbent synthesis and characterization at one end, all the way up to process development at the other end of the spectrum. Breakthrough study nicely sits in the middle of the spectrum, as you can see. So what is a breakthrough experiment? It is the response measured at the exit of an adsorption packed bed due to a step change in adsorbate concentration at the inlet. Pulse input is also possible, but we will restrict our discussion today to step changes only. The adsorbent packed column is adequately regenerated to make it free of any adsorbate as much as possible. The flow controller at the inlet is used to introduce a fixed flow of adsorbate mixed with an inert carrier. The flow meter at the exit measures the exit flow rate. The back pressure regulator maintains the column at the desired pressure. The detector is used to analyze the composition of the exit gas. For the step change in adsorbate concentration at the inlet, which is shown on the first row below the experimental setup diagram, on the left, the right-angled blue line, as you can see on the screen. And we will get a response at the exit, which is a changing concentration of the adsorbate starting from 0, ultimately reaching the same value as the inlet. This is adsorption breakthrough curve. This response contains phase equilibrium information of the adsorbate in the adsorbent for the feed concentration. It also contains information on mass transfer of the adsorbate from the bulk to the pore interior where adsorption takes place. In this talk, we will only discuss phase equilibrium. After equilibrium is achieved with the feed composition, we can withdraw the adsorbate from the feed and allow only the inert gas to flow. This introduces a step change in concentration, which is just the opposite of the previous step change. It will desorb what was adsorbed in the adsorption step. The response at the exit begins from the same feed adsorbate concentration of the previous run and gradually decreases to ultimately become 0. When it comes to 0, it indicates that all adsorbate previously adsorbed has come out. And this is called desorption breakthrough curve. An obvious question at this point is, how is breakthrough study useful? The contributions are at 3 levels. At a qualitative level, it can provide a quick idea of separation potential of an adsorbent for a mixture. I must, however, caution that this apparent separation potential is not a surrogate for the actual separation performance. Quantitatively, it provides useful confirmation of single component equilibrium and kinetic data and can be easily extended to quickly measure mixture equilibrium and kinetics. It uses larger sample size compared to the other methods of equilibrium and kinetic measurements. The breakthrough responses also capture axial dispersion and heat transfer characteristics of an adsorption column. At the process level, the breakthrough study is an important first step. Breakthrough study is used to validate mixture equilibrium and kinetics that constitute the complete process simulation model. It can also be used to validate the process model for every step of a cyclic process. In this talk, we will introduce our breakthrough experimental rig and propose some design guidelines. We will discuss the experimental procedure and analysis of breakthrough response for single component equilibrium measurements and show how it can be easily extended to measure multi-component equilibrium. The schematic on this slide is the detailed version of the simple breakthrough setup we have already introduced a few slides ago. MFCs, the mass flow controllers, help control the feed flow rate and composition at the desired level. MFM, the mass flow meter, measures the flow leaving the adsorption column.
Use your mouse, maybe, if possible.
MS represents an instrument used to analyze the gas composition leaving the adsorber. BPR, for example, these are the BPRs on this diagram, is used to control the pressure level at the desired level. The valves, there are many of them, so it will take time to point to all of them, but you can easily see, are used to guide the flow and introduce step change in concentration at the column inlet. PI, the two pressure indicators, as you see as PI here and PI here, at the inlet and at the exit of the column, they are used to keep track of operating pressure and pressure drop across the adsorber. The column, as you can see, as a whole is immersed in a circulating water bath to maintain the adsorber wall at a constant set temperature. Water cooling is more efficient to remove the heat of adsorption than air cooling. By using an appropriate thermal fluid, we can also conduct in situ regeneration of the adsorbent above the boiling point of water. The vacuum pump is used to periodically pull vacuum while heating, and this enhances the effectiveness of regeneration. TIs are the thermocouples located along the adsorption column length in order to monitor the adsorbent temperature during the breakthrough runs. NV is a needle valve, a small entity right below the arrow, is placed between MFM, that is the mass flow meter, and BPR, the back pressure regulator, to send part of the adsorber exit gas to composition analysis. Now, significance of various color-coded lines. The green lines before and after the valve V4 and after valve V5, they represent the dead volume. It cannot be completely eliminated. It has to be kept as low as possible. The remaining dead volume should be measured and corrected from total response. The red line, again, which is a branch coming out of the valve V4, is used to bypass the column in order to measure the dead volume, and this is called dead volume or blank correction. The purple line right on the top is used to stabilize the flow before introducing a step concentration change at the adsorber inlet. A mass flow controller takes some time to reach the set point, as you all know. This is not a problem when we can allow a long residence time of the adsorbate in the adsorption column. When we deal with a weakly adsorbing system and we only have a small amount of adsorbent for testing, then it is advisable that we use the flow stabilization line. If solenoid valves are used, this can give almost ideal step change without any noise. Step-by-step details on how to use this line are given on slide 11. Now some guidelines. Why we should put the adsorption column in a thermostated circulating bath has already been discussed. We make the following recommendations. Keep column to particle diameter ratio in the range of 7 to 10 to reduce the channeling effect at the wall. Keep the adsorber length to diameter ratio greater than 3. Choose the adsorber length so that the dead volume does not become dominant. Flow control at the inlet and flow measurement at the exit of the adsorption column are must for accurate mass balance. Pressure measurements at the inlet and exit are important for correctly estimating equilibrium capacity. Low flow rates are recommended if only equilibrium measurement is the target. Note that increasing flow rate increases pressure drop and decreases the residence time. Appropriate choice of length to velocity ratio becomes crucially important if we want to extract kinetic information from breakthrough study. The adsorbent should be regenerated in the beginning and periodically between runs. Slowly heat to the required regeneration temperature and alternately purge with an inert gas and pull vacuum for more effective regeneration. The experimental protocol should begin with instrument calibration, followed by column regeneration and dead volume measurement before beginning the breakthrough experiments. First in the protocol is to make experimental rig leak-proof. For leak test, pressurize the column to the maximum pressure level expected in the investigation and ensure that the pressure is held for the duration of the longest breakthrough experiment. Although the flow controllers and flow meter are factory calibrated, the change over time, also the calibration condition at the factory may be different from actual experimental conditions in the laboratory. Hence, in situ calibration against independent standard like bubble flow meter or any other handheld flow calibrator is recommended. Calibrated flow controllers allow preparing various mixture compositions with confidence, and that helps extensively calibrate the detector. Having a stable baseline of the detector for the inert carrier gas, helium for example, is a must. Keep in mind that the baseline may drift in the breakthrough run if it is very long. So baseline drift should be checked and corrected for. Unless we are dealing with very strongly adsorbed gases, purging with the inert gas and pulling vacuum for some time may be sufficient for regenerating in between runs. The dead volume must be measured at the same flow rate and pressure conditions as in the actual experiment, bypassing the column using the red line. If the dead volume correction turns out to be negligible, that is fine, but that should be an informed decision and not an assumption. After leak test, instrument and dead volume calibration, we are now ready to conduct a breakthrough experiment. There are step-by-step instructions on the table. For greater clarity, let us assume that the adsorbate is carbon dioxide and we have a new adsorbent. We have a packed and regenerated adsorption column in place. Initialize the column and the detector by flowing helium. For this, open valves V1, V4, V5, and V6. Open valve 4 from green to green. The BPR and the thermostat are set at the desired levels. The gas will flow all the way up to the vent with a small stream taken to the detector through the needle valve. We will wait until the detector stabilizes at the baseline. We close valves 4 and 6. We prepare the flow and composition of helium and carbon dioxide we want to test and open valve 9 to stabilize the flow. The BPR in this line is also adjusted to the same pressure level used to initialize the column. Note that this flow does not reach the detector, so the baseline we have established is not disturbed. Once the MFC stabilize, we introduce a step change of adsorbate concentration to the column inlet by simultaneously opening valves 4 and 6 and closing valve 9. Again, remember, valve flow opens from green to green. Wait until the detector signal reaches a stable constant value. The bed temperature returns to the initial value. Exit mole fraction of the adsorbate becomes equals to the inlet mole fraction, and the total outlet flow also becomes equal to the inlet. This marks that the adsorbent in the bed is in complete equilibrium with the feed gas composition. On the left of the experimental setup that is under input, what we have is what is at the column inlet, a controlled constant flow of carbon dioxide helium mixture introduced as a step change in adsorbate concentrations. So this is the constant flow, and this is the step change in adsorbate concentration. We want to get the exit. What we want to get at the exit is shown on the right. Carbon dioxide is retained in the adsorbent, and therefore it takes some time to show up in the exit. Until it shows up in the exit, only the inert helium fraction of the feed flow will come out at the other end. So there will be reduction in the exit flow compared to the inlet flow. To see this, you should pay attention to the fact that the concentration is represented by the left y-axis and the flow rate is represented by the right y-axis. Fractional reduction of the exit flow is a good indication of the mole fraction of CO2 in the feed. In the plot, the exit flow rate normalized with feed flow rate begins at 0.7. Again, look against the right y-axis. And this is an indication that CO2 mole fraction in the feed is about 0.3. The exit flow rate will rise along with the rise of the CO2 in the exit stream. This is the beginning of breakthrough. It will continue until the exit flow rate and CO2 mole fraction both become equal to the inlet value. The temperature profiles are not shown here to keep things simple. Results with temperature profiles we will show later. We are assuming that the bed has returned to the feed temperature with the dimensionless total flow rate and dimensionless CO2 fraction at the exit reach 1. We introduced a step change in CO2 concentration, but what we get at the exit is a spread out response. This is a consequence of three things: mass transfer resistance encountered by CO2 to diffuse from the bulk to the pore interior adsorption sites, axial dispersion in the adsorption column and dead volume. It is also influenced by the shape of the equilibrium isotherm. Heat effect is more complicated. Let us skip that for another discussion. At this point, if we want to measure the desorption breakthrough, one choice is to just close valve V2. This will introduce a reverse step change in concentration at the inlet. The desorption run will be at a reduced flow rate. So this is a reverse step change in concentration from previous value to 0, but we have a constant flow rate. If we want to conduct the desorption run at the same flow rate at the adsorption step, then we just cannot stop valve V2 and continue. What we will have to do is close valves V4 and V6 and open V9. Then close V2 to stop CO2 flow and adjust the helium flow to make it equal to the total flow used at the adsorption run. Allow the flow to stabilize and then simultaneously open V4 and V6 and close V9. This results in a reverse step change as I have just shown. The results shown on the right are for helium flow rate that was maintained at the same value as in the adsorption run feed flow rate. Pure helium runs through the bed and gradually desorbs all the adsorbed CO2. Desorbing CO2 is added to the inlet flow rate. So now the flow rate increases at the exit. Again, notice on the right y-axis, the beginning of the flow rate is greater than 1. At the same time, the exit CO2 concentration begins to drop. And as the time progresses, CO2 concentration will continue to drop and eventually fall to 0 when the flow rate will also become equal to the inlet helium flow rate. This marks complete desorption of CO2. For a Langmuirian, that is type 1 isotherm, the shape of the desorption profile is mostly governed by the shape of the equilibrium isotherm and not so much by the mass transfer kinetics. What we measure at the inlet are the constant mole fraction Y in of carbon dioxide and constant total flow rate Q in. At the exit, we measure the changing mole fraction of CO2 and we represent that as YT, and the changing total flow rate as QT. The flow rates are typically in standard liters per minute or some reference pressure temperature conditions. We recommend that we use YTQT normalized with respect to Y in Q in and plot it as a function of time. Since both the volumetric flow rates are at the same reference conditions, the ratio represents molar flow rate at the exit normalized with the constant molar flow rate at the inlet. And therefore, this plot changes from 0 to 1 during the course of adsorption breakthrough run. Now we are ready to analyze the breakthrough results. The adsorption column starts with a uniform temperature as that of the feed and returns to the same state at the end of the adsorption run. So an isothermal mass balance is adequate to calculate the equilibrium capacity of the adsorbent equilibrated with the feed composition, pressure, and temperature conditions. In this analysis, we assume negligible pressure drop in the adsorption column due to flow. This is not a bad assumption unless the column is long and packed with very fine crystals. If that is the case, the analysis will have to be modified to account for pressure drop across the column. We have a constant molar flow rate of the adsorbate at the inlet for the entire duration of the adsorption runs. Hence, the total number of moles in is the molar flow rate multiplied by the duration of the adsorption run, indicated here as T infinity. Infinity is used to remind that we have to give sufficient time for the column to be completely equilibrated with the feed composition. We have a changing molar flow rate at the exit. Hence, total amount out is the integral of that changing flow rate integrated over time from 0 to infinity. The difference between total in and total out is what has accumulated in the dead volume and in the adsorption column. There are two components in the adsorption column: gas composition equal to that of the feed in the voids between the adsorbent particles, plus the adsorbed amount in the adsorbent, which is in equilibrium with the gas in the voids. The rearranged mass balance equations for adsorption and desorption runs are shown on the bottom right corner of the slide. The difference during desorption is moles of adsorbate fed is now 0, and hence the molar flow rate at the exit is normalized with respect to the flow rate used in the adsorption run to equilibrate the bed. On this slide, we graphically illustrate what we measured and how they are related to the mass balance equations just derived. We have agreed to plot dimensionless adsorbate molar flow rate as a function of time. The integral of 1 minus dimensionless molar flow rate represents the mean residence time of the adsorbate. Area 1, shown in red color, represents the mean residence time in the dead volume. So this is area 1. Similarly, area 2 on the right diagram, shown in gray color, is the mean residence time of the adsorbate in adsorption column plus dead volume. Therefore, the corrected mean residence time of the adsorbate only in the adsorption column is obtained by subtracting area 2 from area 1. After obtaining the corrected mean residence time, we can arrange our mass balance equation to calculate the equilibrium adsorbed amount Q in star, as you can see on the second equation on the top, corresponding to the concentration of adsorbate in the feed, which is C in. Each breakthrough measurement provides 1 point, as shown on the diagram C in Q star in on the isotherm, repeat the entire procedure for another value of C in to construct another point and go on like this. The same data may also be obtained from the desorption breakthrough from a similar analysis. If there is pressure drop, replace C in with C average, where C average is calculated based on the arithmetic average of inlet and outlet column pressures at the end of the breakthrough experiment. Note that when that is done, Q star is the equilibrium value corresponding to C average. With that, I would like to pause to take questions. Nicholas Wilkins will be with you when we return to the presentation. Thank you.
Okay, thank you, Dr. Farooq. I have two questions from YouTube. One is from Reza Hakpana. So his question is there, should you be worried about the direction in which the flow is introduced? Should it be top down, or can you also put it bottom up or put it on the side? Is there any?
That's a good question. We have encountered this type of situation when our papers went out for review. At times people say that if you are flowing at a velocity higher than the fluidization velocity, then there is a lot of mixing in the column. So in that situation, the safe argument is flow it downward. But remember that fluidization velocity depends on the particle size, and the way an industrial column is packed is you will have a strainer to restrain the bed at the top, and you will also have very large particles for gas distribution. So calculating the fluidization velocity only based on adsorbent particle is probably not appropriate. In the lab, we never exceed that. So flowing up or down doesn't really matter. And industrial situations, as I said, I think you have other ways to overcome the limitation of fluidization velocity.
The next question comes from Vladimir Bond. It's a very interesting question. Which experimental conditions should be considered for breakthrough investigations when you're using flexible materials, such as MOFs, which have up to 50 to 100% of change in the volume?
Well, that's an interesting question, and that is a question that is outside of my domain because I have never dealt with variable capacity adsorbents. So I think rather than making an off-the-cuff comment, it is probably better that I admit my ignorance that I'm not aware of this situation, what to do.
Yeah, but I think there are also some nice examples about polymers and also coal, which tend to swell, not to this extent. So
you have some experience working with coal, so maybe you would like to share your experience?
No, my experience is more with working with polymers, but not in a column situation. So if you need to know the volume in the system, you have to have some independent measurement. So maybe, and then the challenge that I see is some of these materials are also very sensitive to the gas atmosphere in which they present. So maybe an inert gas will not make them swell, whereas a gas like CO2 or methane might make them swell.
Well, while we are discussing, the thought that goes through my mind is we are talking about equilibrium measurement in breakthrough. And this swelling takes place during the course of the breakthrough study, right? If I understood correctly.
Yeah.
If that is the case, then equilibrium is with respect to what is at the end of the breakthrough. So if all the expansion has taken place, then we know what is then the volume of the adsorbent and the volume of the void, the equilibrium, I think, will represent that end state of the column.
Yep, that's right. Yeah, but it is a challenging situation, nevertheless.
Yes, I agree.
Yeah. So there's a question from Goping Hu. There are two back pressure regulators in your setup. What is the reason for not combining and moving it after the valve? I believe he talks about the needle valve, maybe.
The only reason for that is, as I have probably didn't make it very clear, is then in that case, what will happen is you are going to change the baseline of your detector. I have just established the baseline of the detector from the previous stabilization run. So in order to save one back pressure regulator, all I do is again contaminate my detector with the new composition of the gas. If I may go back to the diagram for a second, if you just combine this together, what is going to happen? The gas will again flow through this Knittel valve, and it will ultimately again contaminate the baseline of the mass spec, which has just been established in the previous step. I hope that is clear, and we can discuss further offline if that is required.
Excellent. I don't have any other questions, but just an announcement that Dr. Farooq and Nick have agreed to stay as long as they can to answer all the questions that are posted. So we can move on to Nick. Nick, do you want to start sharing your screen, please?
Yep. Okay, so can you see the PowerPoint slides and hear me clearly?
Yeah, I can.
Yes, we can see you, Nick.
Great. Okay then. Hello everyone. I would like to start my part of the talk with an animation to show you what happens inside of the adsorption column during a breakthrough experiment. I will take a simple case where the column the experiment is performed isothermally. This is quite difficult to achieve in a gas experiment, but can be achieved in liquid systems. Nevertheless, for the sake of simplifying the situation, the isothermal assumption is illustrative. The simulations are for a 15 mol% carbon dioxide feed in an inert carrier, such as helium. This is for zeolite 13X at 22 degrees Celsius and 1 bar absolute pressure. The inlet flow rate for this experiment also will be 700 ccm. The graphs on the screen show the axial mole composition of carbon dioxide in the top left, the axial solid loading in the bottom left, the carbon dioxide breakthrough profile measured at the end of the column in the top right, and the exit flow rate in the bottom right. It's worth noting too for this animation, the column initially was saturated with an inert component. Okay, so when we start this animation, you can see that as carbon dioxide travels through the column, an equilibrium is established at that point within the column. And initially, we don't see any carbon dioxide leaving the column. All we'll see is the inert gas leaving in the exit flow rate. However, after some time, we will see a carbon dioxide breakthrough. And with that breakthrough, which will start just a couple of seconds here, we'll see an increase also in the exit flow rate. This increase in the exit flow rate will be more dramatic the more concentrated your inlet to the column is. And this also illustrates, again, the need to measure the exit flow rate while performing a breakthrough analysis. So let's look at some experimental examples now. And specifically, I want to look at the comparison of equilibrium measured through breakthrough with static experiments such as volumetry. So here we have two different materials. In the top row, these isotherms are for a metal organic framework called copper BTC. And in the bottom row, we have zeolite 13X. It's worth noting that all of the gray markers in these graphs are for static measurements, static equilibrium points measured through static measurements. So let's start with the top row in copper BTC. From left to right, these isotherms are for nitrogen, methane, and carbon dioxide. So here we have two temperatures that are shown on these plots. The diamonds are for 23 degrees Celsius, and the triangles are for 40 degrees Celsius. The x-axis is shown in concentration of the fluid, and in partial pressure terms, this is from 0 to 2 bar for each of these graphs. So let's look at now the trends for each of these. Nitrogen here we can see is quite linear with increasing concentration. Methane also is quite linear, although slightly a bit more nonlinear than nitrogen with increasing concentration. Carbon dioxide is nonlinear at higher concentrations. So the biggest difference though between all of this collected data is the magnitude of the solid loading on copper BTC. We can see that nitrogen is the weakest component for this, these gases measured on copper BTC, And the largest collected loading is about 0.4 millimole per cc. Carbon dioxide is the strongest on copper BTC, and we can see that we have a loading, our highest measured loading is about 5 millimole per cc. In these graphs, the red points were collected through an adsorption experiment, an adsorption breakthrough experiment, and the blue points were collected through a desorption breakthrough experiment. And what we want to highlight here is that no matter how strong the affinity is to the adsorbent, a breakthrough experiment can match static measurements if performed properly. We see some really good examples here for methane in this region, for nitrogen, and also for carbon dioxide. Okay, so the equilibrium data in the bottom row is for zeolite 13X at 25 degrees Celsius. The plots from left to right are nitrogen, carbon dioxide, and water. For zeolite 13X, nitrogen is quite linear with increasing pressure. CO2 is nonlinear, and water is very nonlinear. On these graphs in the bottom row, all of the black markers are for dynamic column breakthrough experiments collected through adsorption. So as before, good agreement is found for the different magnitudes of loading. This is even true for water, which exhibits a very large loading of approximately 17 moles per kilogram at saturation. The static comparison for these experiments, specifically the bottom row, was volumetrically collected data. Okay, so here we have some single component breakthrough curves for nitrogen in the bottom row and carbon dioxide in the top row on zeolite 13X. These experiments were performed at 22 degrees Celsius in 1 bar absolute pressure. The equilibrium data from the previous slides is also shown. So let's start with nitrogen in the bottom row. 3 compositions are shown. The red, blue, and black curves correspond to 25, 50, and 85 mole percent nitrogen and helium respectively. And what we can notice from these curves, all 3 of these curves in the composition breakthrough and all 3 for the thermal breakthrough, they appear to break through at the same breakthrough time. We see here that this is approximately 12 dimensionless time. It's worth noting that dimensionless time is just the ratio of our actual time to the time it would take an inert component to travel through the column. This is due to the chord that we see on the isotherm from 0 loading to our respective equilibrium point. Here we've shown it for 0 to our red point equilibrium and 0 to our blue point equilibrium. And as you can see, both of these chords lay on top of each other. Because of this, we expect the breakthrough times to be the same. Something else that's worth noting, the compositional breakthroughs for nitrogen appear to be finished at about 30 dimensionless time. Although, if we look at our thermal breakthrough profiles, we can see that that is not true. It takes much, much longer for the temperature at the inlet of the column to reach the outlet of our column. In this case, it takes about at least 300 dimensionless time to see the outlet temperature match the inlet temperature. Also, for a larger step in concentration at the inlet of our column, the more heat that will be generated during the adsorption process. We can see that more heat is generated for 85% nitrogen than 25% nitrogen in this case. So now let's look at the top row, which is carbon dioxide on zeolite 13X, also at 22 degrees Celsius and 1 bar absolute pressure. As seen here, the breakthrough times are no longer equal for the 2 curves that we've shown. This curve in red is for 15 mole percent carbon dioxide, and the curve in blue is for 50 mole percent carbon dioxide. This relates back now to the equilibrium, where we can see the chord from 0 loading, our initial condition, to the respective equilibrium points for our red curve and our blue curve. These no longer follow the same path, and because of that, we expect the breakthrough times to be different from each other. One thing that's also important to note is that the less concentrated our step is to our the inlet of our column, the longer it will take for us to see that step function at the end of our column. We can see it's here with the 15 mole percent breakthrough taking much longer than our 50 mole percent. This is also seen in the temperature profiles. So we can see 50 mole percent breaks through thermally before our 15 mole percent curve. This also illustrates again the fact that it takes much longer for temperatures to return back to the initial condition. We can see maybe about 1500 dimensionless time for our compositional breakthroughs and well over 4,000 for our thermal breakthroughs. So this highlights the point that to obtain good breakthrough data, equilibrium data from our breakthrough experiments, we should continue not just until the composition is seen at the effluent, but also that the temperature at the inlet reaches the outlet of our column. Okay, so let's look at now the relationship between an adsorption and desorption breakthrough curve and their corresponding temperature profiles. We have this shown for nitrogen in the bottom row, methane in the middle row, and carbon dioxide in the top row for copper BTC. We'll start in the bottom row. Nitrogen exhibits a fairly linear isotherm on copper BTC, and therefore, if the desorption and adsorption breakthrough experiment are at the same flow, we'll see that the adsorption in red and the desorption breakthrough experiment will be symmetric. We'll also see this in our temperature profiles. We can see that the maximum adsorption temperature corresponds with the minimum desorption temperature in time, and also that the gain, the amplitude of both are equal. Also, both of them will come back to the feed temperature at about the same time. We'll see similar behavior with methane, although since it's slightly more nonlinear, we see a slight asymmetry now between the breakthrough and desorption profiles. For carbon dioxide, though, which is nonlinear very nonlinear at the point that we've seen, we now have no more symmetry in our breakthrough curves. We can see that the adsorption profile in red is a classic shock transition when the desorption curve in blue is a simple wave. We also see some differences in the temperature profiles. The adsorption profile has a much greater amplitude than our desorption profile has. Also, it takes much longer for the desorption temperature profile to come back to the feed temperature than it does for our adsorption temperature profile. So as Dr. Farooq pointed out at the beginning of this talk, Dr. Seidel Morgenstern had a talk in this webinar series about the relationship of isotherm shape and breakthrough profiles for liquid systems. He also covers a lot of what I just covered in the previous two slides. And if you'd like to learn more about that, I suggest you watch that talk. Okay, so up until this point, we've only talked about single component breakthrough experiments. It's also possible to run breakthrough experiments with multiple components. And before we get started, we want to emphasize why it's important to run multi-component breakthrough experiments. As you all know, there is a limited amount of multi-component equilibrium data in the literature. Often multi-component equilibrium is estimated through ideal adsorbed solution theory or simple extensions to models fitted with single component data. While in some systems these approximations may be reasonable, it's advisable to at least perform a limited validation of mixture equilibrium data using experiments. Multi-component breakthrough experiments can offer insight into competitive adsorption equilibrium and provide validation to process simulations and studies. A multi-component adsorption breakthrough experiment is performed in the same way that a single component experiment is. Some attention needs to be given to calibration of the exit flow rate and composition. And depending on your detectors, the signal might change drastically with different gases. For example, a carbon dioxide detector in nitrogen might give you a different CO2 signal for a given composition of carbon dioxide than it does in helium. The column mass balance is the same for both a multi-component and single component experiment. The difference that we'll see is we now have one of these for every adsorbing component in our mixture. And on the left-hand side, our integral term, the in and out terms of our balance will qualitatively look different for every component in our breakthrough experiment. We've shown this graphically for a binary case. The blue adsorption curve is for our light component, and the red curve is for our heavy component in our binary mixture. As you can see, the heavy component breakthrough looks very similar to a single component, any single component breakthrough experiment. If we put a multi-component step function into our column, after some time, we will see the heavy component leave the column. The light component will leave before our heavy component does. And as we can see in our dimensionless mole flow plot, it will briefly go above 1. And it will stay above 1 until the heavy component breaks through our column, at which point the light component normalized mole flow, dimensionless mole flow, will return back to 1. This part of the curve where we have a dimensionless mole flow greater than 1 is what we call the roll-up. Qualitatively, areas C and A minus B correspond to the heavy and light component integral values in the column mass balance. Area C is quite straightforward to get. It's very similar to getting the integral value from a single component experiment. However, the light component adsorption experiment has some problems. Getting area B can be quite difficult, especially in systems where we have a very large selectivity. For such systems, B might have a similar magnitude in area to area A. If small errors accumulate through your experiment, this could give you a non-real or incorrect equilibrium loading. This often will come from your outlet flow or your composition measurements. So it's possible to conclude in some experiments too, if you have a very large selectivity, that there is no roll-up. This would happen if your detector is not able to pick up the small change in above your normalized mole flow. In these cases, one might be led to believe that there's no roll-up, there's no competition, and because of that, your loading is just area A. However, this is not correct. So for a given set of conditions, we recommend measuring the heavy component equilibrium loading using an adsorption breakthrough experiment and measuring the light component loading using a desorption experiment. So multi-component desorption experiment can be performed immediately after an adsorption experiment, as Dr. Farooq has already touched upon. We would close the mass flow controller to our carbon dioxide and nitrogen, send it through our flow bypass to stabilize the flow of helium, and then open our helium flow to the column at a constant flow rate. The integral in our mass balance now is slightly different. We'll now notice that we have references to the initial conditions of our column instead of the inlet to our column. And this is also true with the loading that we find. Qualitatively, what we'll see, our desorption breakthrough profiles for a multi-component mixture will look like the blue curve for our light component and the red curve for our heavy component. And area D will correspond to the light component desorption integral and for a light component, and area E will be for a heavy component. So area D is a lot easier to measure than the areas A minus B for a light component in an adsorption experiment. And this is why we recommend that you perform a desorption to measure your light component loading for a competitive equilibrium mixture. It's also possible to measure area E, although often this will take a very long time. And in some systems, such as water on zeolite 13X, it might be practically impossible to desorb only with an inert sweep gas. So to reiterate, for a multi-component equilibrium, using breakthrough experiments, measure the heavy component loading using an adsorption experiment at a given inlet composition, and then measure the light component loading using a desorption experiment performed immediately after your adsorption experiment. This will save you time and give you reliable equilibrium data. Okay, so here we have some carbon dioxide nitrogen multi-component equilibrium data and breakthrough curves on zeolite 13X at 22 degrees Celsius and 1 bar absolute pressure. This bottom graph here contains the multi-component equilibrium data as a function of the carbon dioxide composition. The left-hand axis is for the carbon dioxide loading, and the right-hand axis is for the nitrogen loading. It's worth noting that on this graph, the black markers are for nitrogen measurements and the red markers are for carbon dioxide measurements. In the top row, we have our corresponding adsorption breakthrough profile for carbon dioxide, and the highlighted area is the integral value for that experiment. And I should make this absolutely clear. These were for actual experiments that we performed in our lab. This loading, as you know, can be used to then find the equilibrium loading, or this area, the integral area, can then be used to find the equilibrium loading. We also have the corresponding desorption experiment for nitrogen, where we can see the desorption curve in black and the integral area for the mass balance highlighted in black. Okay, so for this, we can use these areas as explained previously to find our equilibrium loadings highlighted on the graph here. This was for a 50-50 carbon dioxide nitrogen experiment. And for 2 experiments, our adsorption and desorption experiment, we get 1 set of points at a given composition. It's worth noting that these calculations were performed for every set of points on this multi-component isotherm. With post-combustion carbon capture being a popular topic at the moment, many researchers want to perform humid carbon dioxide breakthrough experiments. So we've shown a couple here on the slide. We have a set of humid carbon dioxide breakthrough profiles. On the left, we have carbon dioxide breakthrough, compositional breakthrough. We have the water compositional breakthrough in the middle, and we have the temperature profiles on the right. One thing that's worth mentioning here is look at the breakthrough times for water compared to carbon dioxide. We can see that for water, it takes about tens of thousands of dimensionless time for water to leave the column. However, for carbon dioxide, it only takes 100 dimensionless time. So often what we'll see is for a humid carbon dioxide experiment, people will use this competitive carbon dioxide curve as proof that water does not affect the carbon dioxide loading in this process. As you can see, all of these break through, all these different compositions break through at the same time. And if we were to compare this to a single component carbon dioxide breakthrough experiment at the same conditions, we would find a very similar breakthrough curve. However, this fails to account for the carbon dioxide rollup and subsequent water breakthrough. So 2 aspects require attention. The first is that at ambient conditions, a stream of gas, 100% relative humidity, will only contain about 3 mol% water. This means that the carbon dioxide rollup for a binary system will not be very dramatic. And as we can see in the CO2 plot, I had to blow up this area from 96 mol% to 100 mol% to be able to clearly see these rollups. The second consideration is that water travels very slowly in these experiments through the column. And as water vapor travels through the column, it will push out carbon dioxide and replace it with water. So I've prepared an animation to highlight this previous point and also to show a non-isothermal simulation of a multi-component breakthrough. This is for a 99.1 mol% mixture of carbon dioxide and water at 22 degrees Celsius and 1 bar absolute pressure on zeolite 13X. For this animation, the bed was initially saturated with an inert gas. The top row is the axial composition of water and the breakthrough curve for water at the end of the column. The next row is for carbon dioxide, and here we have the axial composition of carbon dioxide and the carbon dioxide breakthrough profile at the effluent of the column. It's worth mentioning that I will be showing water in blue and carbon dioxide in red. The third row is for the temperature. We have the axial temperature profiles here on the left and the temperature breakthrough profile on the right. These will be shown in black. For the final row, we have the solid loading of both water and carbon dioxide, shown in blue and red respectively, and the exiting flow rate. So notice in this animation that carbon dioxide leaves the bed almost immediately compared to water. We see a spike in temperature as carbon dioxide adsorbs and breaks through the column. At this point, water has barely entered the bed. We can see this here with our inlet composition of water. It has not even made it through 10% of the bed. And in the loading profiles where water is, again, barely penetrated the bed, carbon dioxide has essentially seen the column as a fresh column with no water in it. If we continue the simulation, we'll see that is over time, water will progressively kick out carbon dioxide. And after a very long time, we'll notice the water breakthrough at the end of the column. And at this point, carbon dioxide rollup will end. Once the effluent temperature matches the inlet temperature, equilibrium has been reached. And we'll notice at this point that the carbon dioxide loading is very small compared to what it was before. And now the entire column is almost saturated entirely with water. Okay, so we have two figures on the screen here, and both of these are for multi-component mixtures on zeolite 13X. The one on the left is for carbon dioxide and nitrogen, and the one on the right is for carbon dioxide and water. All of these were done at 22 degrees Celsius and 1 bar absolute pressure. And all of the markers shown on the screen were collected either through dynamic column adsorption or desorption breakthrough experiments. Let's start with the figure on the left. I have shown also some lines. These lines are IAS, ideal adsorbed solution theory, predictions for carbon dioxide in red and nitrogen in black. From these lines, we can see pretty clearly that IAS fits the carbon dioxide very well in this mixture. However, it fails to capture the multi-component equilibrium of nitrogen. We can see that there's a large underestimation for these conditions. On the right, we have, again, carbon dioxide and water. However, these lines now are not from ideal adsorbed solution theory. These are just some empirical fits that we had to a semi-empirical modification to the dual site linear isotherm that we use to do some process studies in our paper, and also to generate the simulations on the previous slide. So one thing that I want to emphasize now in this slide is, again, it is fairly straightforward to measure the heavy component equilibrium loading for systems where we have very extreme competition. However, we run into some complications with our light component in these mixtures. And someone might think that measuring the light component equilibrium loading might not seem important, especially if you're looking at carbon capture as an example, where we want to capture carbon dioxide, not nitrogen. However, often, while it might seem insignificant, these have rather large implications in process simulation and process studies. I would refer to Arvind Rajendran's talk on May 14th, where he'll elaborate more on these points. As Dr. Farooq stated at the beginning of the talk, we've only covered a small amount of what dynamic column breakthrough experiments are able to do. Specifically, we focused on how to perform a good breakthrough experiment and the interpretation of single and multi-component equilibrium experiments. Dr. Farooq, Arvind, and I are preparing a review paper for the diffusion topic issue for the Adsorption Journal that will greatly expand on what we're able to cover here today. We'll go into detail on kinetic and diffusion information that can be taken from the breakthrough curves. We'll talk about details of heat transfer that we weren't able to cover, and how to model and simulate dynamic column breakthrough. And with that, to conclude this talk, I just want to point out a couple of things that I wish I knew when I started using and studying dynamic column breakthrough. Calibrating the exit flow is extremely important in both single and multi-component experiments. Breakthrough is a molar flow that leaves your column, not just your effluent mole fractions. In multi-component experiments, proper calibration of a mass flow meter can be tricky since a change in composition at the effluent will change the exit flow signal. Concentration detectors often will give you different signals when your test gas is in a different carrier gas. For example, for a fixed relative humidity, the relative humidity probe that we have in our lab will report a much smaller signal for water in carbon dioxide than it does in air. Also, breakthrough is not finished until the effluent temperature is the same as our inlet temperature. The system has not reached an equilibrium until this point. This is very easy to spot if you look at it on a dimensionless mole flow plot like we've suggested in this talk. The last consideration is dead volume should be as small as possible. It's easier to measure, or it's easier to correct a breakthrough curve if there's a minimal amount of dead volume. All of these suggestions can significantly affect your calculated loading. And with that, I'll leave you with some references. Thank you for your time, and I'll ask if you have any questions.
Well, thank you, Nick. We have a few questions from YouTube, and I would ask participants to post their questions as we go.
Okay.
So the first one comes from Arashdip Singh. So he talks about the same issue that you had mentioned about. For multi-component gases, the exit composition will change. And how do you make sure that your mass flow controllers are able to accurately measure the flow?
So there's a couple ways that we've looked at this. In both of the papers that I've published on this, we've essentially just calibrated it using different mixtures of gas. So we would maybe for a carbon dioxide experiment at, let's say, 50-50 carbon dioxide nitrogen, we would run essentially calibration curve for that composition, 100% carbon dioxide and 0% carbon dioxide. And by that, I mean pure nitrogen. And we do the same in helium mixtures as well. And from that, you can then essentially determine the slope of your calibration plot based off of one of your components in the mixture. This way is a bit tricky to do. We'll elaborate on this more in our paper as well. One way that I believe Dr. Farooq brought up in the first part of his talk is you can use a tracer, such as helium, in your experiment. So you will know that whatever signal you're getting during that point for helium would correspond to a given outlet flow. But I haven't tried this way myself yet.
Yep. Dr. Farooq, do you want to elaborate on that maybe? You have to unmute, please.
Okay, what Nick said is absolutely correct. If you are using a mass flow meter, then you have to calibrate very carefully. If you go to the manual of the mass flow meter, they will give you equations for mixture flow rate determination. So all you have to do is to measure flow rates at different compositions and back out some of the constants that govern those equations. Simpler way out, but which is expensive, is to use Coriolis mass flow meters. That is not dependent on composition, so you are safer. And what we have tried in our lab on a limited scale is if you do not have any way of measuring the exit flow, at least use a small flow of helium in your feed gas. Never use just pure adsorbates, and use that helium flow rate, assume that it roughly remains constant throughout your breakthrough, and that can give you a rough indication of your exit flow rate. That will not be as accurate as measuring using mass flow meter or Coriolis meter, but it is better than not measuring at all.
Excellent. So the next question comes from Marcus Mello. What is the best position to locate the thermocouple to measure heat effects when you're measuring breakthrough curves?
We've actually, in our lab, we've done it in many different positions. I generally put one, if you have just one, somewhere near the end of the column. But you have to ensure that the thermocouple is still touching the solid. It can't be outside of your column. This way, you'll actually capture the thermal breakthrough wave traveling through your column. But we've done this in our lab, other experiments where we've had multiple thermocouples throughout our bed to see how the temperature waves are going through your process. But at least in my experience, I've always put it near the end of the column if I only have one. And I don't know, Dr. Farooq, do you want to add to that?
No, I agree. If
Okay.
the objective is essentially to only look at the heat effect and not do any theoretical modeling, then placing anywhere is fine. But if we want to do the modeling, then we have to make sure that our discretized model does have a point where the thermocouple is.
Yes.
And therefore, you will have to take that into consideration before, even if you start your experiment.
But if you're just
So
doing this for
0.5,
equilibrium,
0.75, 0.25, these are the safer places.
Yeah, the other, maybe if I could just add to that, the other aspect that we see is, especially if your columns have end fittings, very heavy end fittings, they tend to be like thermal masses. So when you're trying to compare at a more quantitative level with, for example, models, you have to be careful in taking those into account. At the end, you might be left with nothing but to fit your heat transfer coefficients in some way. So the next question again comes from Marashdeep Singh. Maybe I'll ask Dr. Farooq to take this first and then to Nick. Does industrial separation units work under isothermal conditions? If not, why are we doing all these experiments under isothermal conditions? I think it's a very nice question.
Well, there are two things to this question. Industrial processes, if the diameter is large, definitely does not work near isothermal conditions. But we are doing isothermal experiments to first of all establish without any dispute the equilibrium and kinetics. And once we have established that without any dispute, then we can of course take up non-isothermal study. That's not an issue. But industrial processes in most cases are more towards adiabatic. So that is again the extreme conditions. So even by doing non-isothermal study where the heat transfer coefficient is between the adiabatic and isothermal limit, you do gain some insight, but you do not fully understand how is it going to behave in the industrial scale. To sum up, the whole point here is isothermal study has its role to establish equilibrium and kinetics. Heat effect does not completely destroy the need for that. Heat effect does have influence on the process performance, but it does not completely negate our understanding that we gain from equilibrium and kinetics.
And also, I think at a laboratory scale, no matter how hard you try, it is very difficult to make your columns adiabatic as well. Yeah. Nick, do you have anything to add?
I fully agree.
No, I agree with that. I have
Excellent.
nothing to add to that.
Okay, I have more questions coming in. So this is from Ing Xiong. Thanks for the talk. I have two questions. Do you recommend to pressurize the column to a pressure higher than the ambient when doing breakthrough measurements?
I guess it depends on what you're studying, and I wouldn't, I guess, pressurize. I would regulate the pressure with a back pressure regulator. So in that case, if you were measuring at a higher pressure, if you wanted to, let's say, operate at 2 bar, you would essentially tune your back pressure regulator to be at 2 bar. And I believe you would also, when you're stabilizing your flow, use a back pressure regulator to get that flow up to a stable 2 bar before you send it to your column. Dr. Farooq should probably add to that because I've only actually run experiments at ambient conditions.
It depends what is your target. If your objective is to, for example, we know that measuring CO2 isotherm, which we have done a lot, beyond atmospheric pressure is not really important for the industrial process we are trying to study, right? So their atmospheric condition breakthrough is fine. But if my objective is to study, for example, the other system that you are studying is natural gas upgrading, the whole process is at very high pressure. And if you want to understand that, and if you want to extract equilibrium information, then you have to pressurize your column.
Exactly.
Because
yeah.
even if you take the pure methane, the pressure will be maximum atmospheric, but in an industrial process, the partial pressure of methane will be much higher than atmospheric. And then
Exactly, yeah.
second thing is, if we want to study kinetics, there may be need to do experiments at different pressure conditions to understand the transport mechanism. So there is no straightforward answer whether it should be done at atmospheric or above atmospheric level. It will depend on what is the scope of your study.
I have two questions related to humidity coming up. I'll ask Ying Xiong's question first. So how do you set up the breakthrough instrument to control humidity in your gas flow so that you can ensure that you have a constant flow of a constant humidity?
Okay, there are a couple ways to do this. The way that I ended up doing these in my experiments was using what we call a bubbler. So essentially you have a volume of water and you inject your gas, whatever gas you want to test. In my case, it was just carbon dioxide, into the bottom of the bubbler, and you let the carbon dioxide go through your volume of water, and then the effluent becomes a humid stream. You can then dilute it with more fresh carbon dioxide after this process to get a desired relative humidity that you want. There's generally a long transient with this before it hits a steady state in the effluent water humidity. But you're able to do this. So essentially you just have to add extra time to the beginning of your experiment to have to prepare your humid gas. There's another way to do this that I'm familiar with, which is a constant evaporation mixer. So essentially you have a flow meter that gives you liquid water that's programmed to essentially to flow this water into a gas stream. And essentially, depending on your gas, you would do some math a priori and then control that flow rate to give you desired relative humidity. These, though, I think work better at higher temperatures and very large flow rates, where a bubbler, you can still get a fairly low flow rate. You just have to overcome essentially the amount of water that you have in your system for flow. And I'm not sure, in your lab, Dr. Farooq, have you prepared humid gas in the same way or another way?
We have experience of using bubbler, as you mentioned. So you saturate completely. And there is some control there also by immersing that bubbler in a thermostat. You can also control the level of humidity that you want to achieve. Even if it is 100%, if it is done at 20 degrees versus 40 degrees, that will give significantly different amount of moisture. And then you can combine the stream to control to any level you want. We have also the experience of using a membrane humidifier, which is very similar in concept. You basically use water at different temperature and control the flow on the other side of the membrane. And depending on the temperature, the humidity level is going to be different. So I think the bubbler method works very well. As you pointed out, it may have a long transient, but it is simple, cheap, and by mixing streams, you can have significant freedom of varying them over a wide range.
It's very easy to build a bubbler too. I've built a couple in the course of my experiments. All you need is a tank and some valves, and I usually put a check valve at the end so you don't accidentally send water through your system, and you have a bubbler.
Yeah, if I may add just a couple of points to that, Nick. The other aspect that we have noticed is also some of these humidity sensors have a long response time. So you have to be aware of that. And secondly, it is also very critical to measure the actual humidity that comes out of the bubbler so that you know what is the humidity that is coming out. Thirdly, in some of these capacitive humidity sensors, depending on what you use, are also sensitive to the CO2. So if CO2 is present, then it shows a very different reading. So it is very important to calibrate it a priori. I can also refer you to a nice paper by Max Hefty and Marco Mazzotti, where they also talk about the challenges that are involved in running experiments with water. So the next question comes from Marco today. Does the fact that water travels much slower than CO2 in the bed means that it would be accumulated over several cycles? I think he's talking not about just one breakthrough, but repeated breakthroughs, gradually reducing the CO2 uptake. So if provided regeneration conditions do not remove the water from the bed. If yes, does this mean that proper adsorbent evaluation for capture from humid should necessarily involve many cycles, example in the order of 100, or in order to avoid drawing wrong conclusions?
So there's a couple ways to look at this. You are correct that with like Zeolite 13X, that it's pretty difficult to remove water from Zeolite 13X using just a sweep or even just pulling pressure, a deep vacuum, because it's such a rectangular isotherm. In these cases, I've seen people, there's another paper by Max Hefty and Marco Mazzotti about TSA cycles for essentially a cycle with Zeolite 13X. And in this case, you use a temperature swing to end up removing water from these cycles. I also know that Dr. Farooq and Arvind have a paper where they've looked at maybe staging a process where you would have silica gel before to remove water, and then you'd send essentially a 90 your mixture of carbon dioxide and nitrogen to a Zeolite 13X bed where you can then perform the separation.
Dr. Farooq, do you want to comment on that?
Well, this creeping front is a very well-known problem in adsorption process study. Before we came to the CO2 capture challenges, the previous known similar case was hydrogen purification from a refinery fuel gas, which has got C1 to C4, C5, let's say. And there is where the first time we started seeing the dual bed concept. If you had used only activated carbon, which was the main adsorbent for removing the hydrocarbons, the problem would be it would work very well for C1, C2, but C4, C5 would hardly come out. So not only hundreds, but after a few thousand cycles, the hydrocarbon may start breaking through at the other end. And to overcome that, what has been done is they have either used silica gel or alumina, which has got shallower isotherm for the higher hydrocarbons. And you never allow this higher hydrocarbon to penetrate the carbon section of the bed. Yes, so moisture can have similar challenge. It may apparently look like it is not coming out for a long time, but after a long time, the whole column may break through and the moisture may start coming at the other end.
Excellent. So the next question is from Arthur Moretti. My question is, are glass beads a valid option to reduce the volume? So when you have dead space, for instance.
So I'm guessing you mean filling a column with glass beads and having a small section being adsorbent. If that's the case, we've run a couple of experiments like this in our lab. And what we've noticed is, depending on how big the upstream dead volume is, you might not see a difference. But if you have a large section after your adsorbent column, this will give you some mixing problems and could actually end up making your dead volume very large. If you're talking about in terms of piping, glass beads, I think would be quite hard to fit into your piping up to your column, and it would probably add significant pressure drop issues to your column. We'll see even with beaded adsorbents that sometimes they'll get jammed in the pipes of our DCB experiments, and the pressure drop becomes sometimes so large that you'll get very, very weird breakthrough profiles compared to what you're expecting.
Dr. Farooq?
Nick has covered almost all the practical issues. It is not clear to me what is the objective of using glass bead. I mean, if you think that you have a large column and you are not able to fill it up with adsorbent and you want to fill it up with glass beads and put the adsorbent in the middle section. For equilibrium measurement, I don't think it will be a problem because the shape of the breakthrough is not particularly important to you. So if you make the correction, but the only question is if you have glass bead before and after your packing section, how are you going to do the bypass lining? Bypass has to be returned before the glass bead. If you cannot do that, then you are not characterizing your dead volume correctly. Second issue is if you want to extract kinetic information by putting glass bead before the adsorption column, you are going to introduce a bit of dispersion to the feed that is coming into the column. That is something that can never be corrected. That has to be considered in your modeling. And what Nick has already pointed out, if you have glass bead downstream of your adsorbent bed, then that may introduce a bit of mixing. So there will be some distortion in your breakthrough profile. And as I said, unless your blank run returns before the glass bead, you will never be able to correct that. So we will have to be careful when using glass bead to reduce the need for adsorbent to fill a column.
Yeah, if I may just add to that, the other case where instead of the glass beads, you might also be in a similar situation is if you're trying to measure breakthroughs at very high temperatures, and if you are worried that your detectors could be affected because of the high temperature, the natural idea would be to have a very long line that goes into a furnace, and you have a very small amount of sample that you might want to characterize. So then you have to be aware that there is so much volume that is besides your adsorbent volume that might start dominating the retention time. So if you're trying to show how well separated your two components are, then you might actually underestimate the capacity of your adsorbent because your retention times end up being entirely dominated by the dead time, not by the time in your column. So again, to reemphasize that it is important that you know how much of volume there is. If you're trying to also establish kinetic parameters or to show how fast the mass transfer is, all of this could end up distorting your profiles. So the next question is from Praveen Bosco. Thanks for the talk. My question is about how important is it to consider the lag time in the measurement of the breakthrough in our analysis? So I think we have spoken about the lag time in terms of, oh no, I think he's talking about the analyzer, the lag time in the analyzer.
Well, this would be part of your dead volume response. If you perform a dead volume response with, let's say, a bypass around your column, it will still take some time for your detector to receive that signal. And if you're using the same detector, you should have measured that with your dead volume, your blank curve response.
Yeah, Dr. Farooq, do you have
Yeah,
anything to add?
Nick is spot on. So the blank response does take care of whatever dynamics you have, including the lag in the detector.
And sometimes if your detector works on the difference in the concentration, you might also find that very low concentrations might take a much longer time as well. So the next question is from David Madden. Do you have any recommendations for performing breakthrough experiments with C2 gas mixtures, especially if you have to detect a change in gas mixtures with very similar mass spectrums?
I've not worked in this, so Dr. Farooq, have you worked in C2?
Well, you're having problem with detection?
Yeah, where the mass signal for the two components are very similar.
Well, then if the mass spec doesn't work, then we may have to take the difficult route. If there is any column which is going to separate them, then we may have to draw samples and do chromatography.
Yep. Excellent. I think I don't see any further questions. So I think we have come to the end of the questions here. So I will turn over control to Dan Siderius.
I'll stop sharing my screen.
Thank you, Farooq and Nick, for your outstanding presentation on the design and interpretation of breakthrough experiments. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. Please join us on Tuesday, May 12th at 2 p.m. Tokyo time, which is 7 a.m. Central Europe and 1 a.m. in New York, which is about 14 hours from now, for a webinar on the use of carbon materials in adsorption presented by Professor Katsumi Kaneko of Shinsu University. Please note the time difference, and I hope that you can join us, whether live or recorded on YouTube later on. Please join us for other seminars this week. Stefan Kaskal and Arvind Rajendran will present this week, and then we'll have our final webinar in this series, Camille Petit, on the following Monday. Thank you, and we hope that you have a wonderful day. Goodbye.